Thank you very much. And also, I want to thank the organizers to invite me to this nice seminar. So this is a joint work with Katsumi Eto, and just we submitted it to archive very recently. But at the same time, since we are in haste, so we found several errors in but so going to revise it soon. And the latter part is joint work in progress with Eto, Naoiki Matsuoka, and Takahiro Numata. And okay, then so this is today's talk. Introduction and review on numerical semigroups and semigroup rings, and inverse polynomials, and then symmetric semigroups with small multiplicity, and then unique factorization and complete intersection, and growing and inverse polynomial, and another proof of Brzezinski's theorem for Gorenstein cage of -3. Okay, so this research was inspired by the talk of Marilina Rossi, titled A Constructive Approach to One-Dimensional Gorenstein K-Algebra. At this virtual commutative algebra seminar on Tuesday, December 1st, 2020. The talk was based on her joint work with Fan Elias, the structure of the inverse system of Gorenstein K-algebras, and constructive approach to one-dimensional Gorenstein K-algebras. So the aim of this talk is to introduce the theory of inverse polynomials of Macaulay to the theory of semigroup rings of numerical semigroups. So actually, before I attend this talk of Rossi, so I didn't think we can use theory of inverse polynomial to theory of numerical semigroups, because I thought inverse polynomial is, of course, very useful for Artinian rings. And of course, the numerical semigroup rings has dimension 1. And so I am very grateful to the organizers of this seminar. So without this seminar, this work has not started yet. And we are also very grateful to the gap system. So without this system, we could not accomplish this work. We compute very frequently, and then so this theory is made by many computations. Okay, let's start with Gorenstein-Artin algebra and inverse polynomial. Let S is a polynomial ring of E variables over a field K. We always consider S as a graded ring, putting degree xi to ni, and we put M to be the unique maximal graded integer here, and E to be the injective envelope S over N over S. Then by Macaulay, we can consider E as a set of inverse polynomials over K. Namely, is a polynomial of large x1 to capital X1 to capital Xe, and we consider capital Xi to be the inverse of small xi. And where we define the action of S on E by this formula, namely, if some I is bigger than Bi, then the product will be 0, and otherwise they are given by the subtraction. And if I is an n-primary ideal of S, A equal S over I is an Archian, and injective envelope of A over N over A is given by home of SAE, namely the annihilator of I in E. And in particular, A is Gorenstein, if and only if. So EA of AM over M is the principal. And conversely, given an inverse polynomial J, AJ is S over annihilator of J, is a Gorenstein-Archian algebra. In general, annihilator I is generated by type A inverse polynomials. So it is a very well-known theory of. Okay. Then H is called
there is no sound coming. I think there is.
it's okay.
Now it is okay.
Okay.
Yeah, yeah.
Okay, thank you. And what's yeah. And so I okay. H is N1 to NE if so, just a moment. So yeah. And sorry. Okay. Sorry, some bad thing is happening in my computer. And
Yeah, you have to keep volume of one device completely off.
yes.
Yeah, mute the other device.
Oh.
So there is still some resonance. You can mute the controls in one device, but keep them on in this device where you are using slides.
Yeah. So full screen. Huge. Okay. Okay. So we write H in N1 to NE if H is minimally generated by N1 to NE. Is it okay now?
It is okay now.
Okay, thank you. And for H and the field, let KH be the semigroup ring. And so phi H is a natural surjection from S to KH. And we write the kernel by phi H. For H in H, dimension of KH over T to the H is always H, and the base is given by Appel set APAH HH equal N in H with N minus H not in H. In particular, the multiplicity MH is the minimum of positive element in H. And the largest number F in not in H is called the Froebel's number of H. and denoted by f of h. Also, we put pfh, the pseudo-Frobenius numbers, the set of f in z minus h, h plus, f plus h plus is included in h. So these concepts are closely related to H1 local homology of KH. So numerical semigrouping is very good objects in commutative algebra. So namely, from the exact sequence KH in H and K T inverse and K of Z minus H. And so we consider this to be a factor module. And we see that Frobenius number is just equal to the A invariant of KH introduced by Goto and myself. A invariant is max of n. H1 MKH has a degree of H1 MKH is not 0. Also, we have Soku is corresponding to pseudo-Frobenius numbers. Okay, so these are the written in Goto Watanabe graded rings 1. And hence we have type is H is type KH, it's Frobenius number, and a canonical module of KH is so just dual of H1 and just equal to generated by minus of Z minus H. Yeah, so canonical module of KH is generated by T to the minus X, where X is in Z minus H. And also for H, in H, we have A invariant of KH over T to the H is maximum of H non-zero degree, and this is equal to FH plus H by the general theory of A invariant. And Soku is generated by T to the F plus H. F is in pseudo-Frobenius number. So the following order relation is very important in our theory. So for n and n prime in Z, we denote H is larger than n prime in H if and only if n minus n prime is in H. We recall the notion of groupings of numerical semigroups H1 and H2. So grouping is for numerical semigroup H1, H2, and D1 in H2, D2 in H1 with D1, D2 relatively prime, which are not generators of H2, H1. We call H is generated by D1 times elements of H1 and D2 times elements of H2. So this is called grouping. And grouping is KH is in the subring of K to the T1, and KH2 is subring to KT2. Then, so KH is obtained by tensoring KH and KH2 over K, factoring by a non-zero divisor T1 D2 minus T2 D1. So inputting degree T1 is D1 and degree T2 is D2 in KH. Yes, we have type is because this is tensor, type is product and pseudo-Frobenius number is computed in the general theory of graded rings. In particular, we have Frobenius number of H is written by D1 times FH1 plus D2 times FH2 plus D1 T2. note that so KH is Gorenstein if and only if so are H and H2 and the same with a complete section. Also note that if H2 equals n itself, then Fn equals -1, and hence we have Schroeder's number of D1H and D2 is D1F plus D2 times D1 minus 1. Okay. Okay, now, so we have inverse polynomials. We talk about inverse polynomials. So if H is generated by N1 to Ne, so we call, so H is the equal sum of Ai Ni, a factorization of H. So with one factorization, we attach the monomial, so product of Xi Ai in S, and also so large M is product of capital Xi to the Ai in E. And the corresponding inverse polynomial is so J of H equals sum of all the factorizations of H in A. So for example, so let H be 5, 6, 7, 8, and we write so x1, x2, x versus x, y, z, w. Then we know that Schroeder's number is just 9. H is Gorenstein, and J of H 14. 14 is Schroeder's number plus 5, and 14 is factor as 6 plus 8, and also twice 7, and written by YW plus D square, and H, for example, H19 is X times YW plus Z prime, and also Y square times Z is so added. And so the second H is 8, 12, 14, 19. And then Froebel's number is 37. And J of H 45 is 37 plus 8. And then YZW, this is a unique factorization. Hence, so I have not spoken about that, but IH plus X is X, and so YZW annihilator, Y square, Z square, W square. Okay, such is which we are going to do. Okay, so first let's describe IH by inverse polynomial. Well, let X equal N1 and so take A into N3A, and with H equal degree of X to the A. Then IH plus X to the A is intersection of annihilator of J of H, F plus H, where F runs all elements of Schroeder's numbers. So hence in particular for each Ny, IH plus Xi equal, so annihilator, intersection of annihilator of J, H, and F plus Ni, so F is running for every element in Froebel's numbers, Schroeder's numbers. In particular, if H is symmetric, then IH plus XI is just annihilator of J of H, FH plus NI. I forgot to add Xi on the right hand side, sorry. And so for the mu means the number of generators of IH, and it is very important. So and so mu is the same with when we divide it by xy. So we can see the number of generators by this formula. Also, okay. To prove the theorem, so first we see a lemma. So let h equal n1 to ne. So m is in h a with some. So h is degree of x to the a. Then we have, so if h is not less than m in h, then xa times j of hm equal j of hm minus h. And otherwise, if h is not less than m in h, then xa times j hm equals 0. So thus xs is annihilator. So hence annihilator is generated by IH, and so x to the a, where a degree of a is not less than m in h. And we have degree in large letter, the capital letter means the set of degrees of non-zero element of inside. So non-zero element of S over annihilator of SJHM is just the H in H. So H is not H is less than M in H. And since H is in degree, if and only if MI H is so in degree of S over annihilator of G7. So by the argument we are doing, so the dimension of S over annihilator of SJHM is even. So because there is duality, so except in the case M is even and half of M is H. Only that part, so duality gives odd number. And so remarks, AB is NE, it gives the same degree, H then XA minus XB is in IH by definition, and IH plus XA equal, of course, IH plus XB. So, okay, now, so we prove the theorem. So this theorem is 3.3. IH plus XA is written as intersection of annihilators. First, we show that IH plus XA is included annihilator of S, J, H, comma, F plus H for every F in pseudo-flat number. Since H is not less than F plus H in H, because F is not in H, XA is annihilator of J in F plus H by element. So take a generator XB minus C of IH, where BC the same degree, we may assume that D is less than F plus H in H, since otherwise XB or X to the C is in annihilator. Then by lemma 3.5, so XB minus XC, so by lemma 1, so this is the same, gives the same thing. So if we subtract them, it gives 0. So in any case, XB minus XC are in annihilator. So therefore, AH plus XA is contained in annihilator of J of X, H, F plus H for every pseudo-price number F. So since we have shown that IH plus XA is in intersection, we have a surjection and note that if for B in an E, the image of XB in S over IH plus XA is not 0 if and only if degree HB is not in H plus H, namely if degree X to the B is in Appel set. Then there is some, by the definition of pseudo-Frobenius numbers, so if something is not in H, then that thing is less than in H to the F with some F in pseudo-Frobenius number. So satisfying degree H if B is less than F plus H in H, and hence XB times J of F plus H is J of H F plus H minus degree B, not 0 by lemma. So this shows that so the surjection is also an injection. Okay, and we have also a criterion for almost symmetric semigroups. But before going there, so we give an example. So let H be 8, 12, 14, 15 with FH is equal 33. We put S equal so X, Y, Z, W. And since so N1 is 8, so FH plus N1 is 41. It's 12 plus 41 is a unique factorization of 41. J of H41 equal Y, capital YZW. And IH plus X H plus H equal Y square Z square W square. So I'm sorry that I did not write plus X. I should write plus X there. And we can show that X of J of H comma is missing. FR plus H is monomial. Sorry, FR is that FH, so Frobenius number plus H is a monomial for some H and plus if and only if H is free in the sense of Rosales and Garcia-Sanchez famous book of numerical semigroups, which is a special type of a complete succession. Okay. And second, so H generated by 7, 11, 16, 19 with, with F, H equals, F, Frobenius number is 13, 31. 33 is not long. And then since 38 is 31 plus 7 is, and so annihilator is this. Oh. And so we can see that the dimension of S over annihilator is just 7, just N1. And also, let H be 9, 10, 13. And then Frobenius number, pseudo-Frobenius number is 17 and 34. And H is almost symmetric of type 2. And since 34 is double of 17, this is pseudo-symmetric. And we can calculate so J of 26 and 43 and putting at IH plus So we know that the IH can be written in this maximal minus of this form. Okay.
Sir, can I disturb you for a moment? This is Sridevi.
Sorry?
Yeah, I have one question. So how do you get this JH38 in the example 2?
Example 2?
So what is the trick to find this JH, 38?
J of H 38?
Yeah. So this y square z
okay.
How do you compute this?
Usually we compute by gap.
Okay.
So in this case, we could do that, but so we should treat Frobenius number is 200 something or so, and then so Pedro, will you explain?
Yeah, thanks.
Yeah,
yes, you just compute the factorizations and offset with respect to the minimal generator. And from these factorizations, you take the monomials, corresponding monomials, and sum them up. And this is your
that's what I'm guessing here. Like this is like 2 into 11. So this plus y to the power 2, and then 16 coefficient is 1. So that's why it's 1, y square z, right? Is it?
That's it.
Okay. Thanks.
Yeah, so Pedro is one of the leaders of the GAP, and so it is very nice to see. Thank you. Okay, so Pedro is one of the authors of the famous book, Numerical Semigroups, published by Springer. Okay. And sorry. And we go to number 3, 9, 10, 13. So in this case, so we see that dimension of S over annihilator of S43 is 8. But we noted that N1 is 9. So this difference comes from the type of H. And so this is type 2, and so the difference is just 1, means this H is almost symmetric. Okay, so this is okay. Sorry. We are doing next. Sorry, not yet. Okay, so we define almost symmetric semigroups. So the gap of H is written by G of H. then we see H is symmetric if and only if twice of gap is Frobenius number plus 1. So in general, we have twice of number gap is not less than Frobenius number plus type H. And we say that H is almost symmetric if twice of GH is equal. Yeah, this is equality. F H plus type H. This condition is equivalent to say that, so if we divide by the canonical module by the principal module generated by this, so then this is analyzed by the maximal ideal. So thus almost symmetric is and the almost Goranstein. Yeah, so almost symmetric and almost Goranstein is the same thing for semigroup rings. And then the theorem, if H equals N1 to the NE, then for any H plus, we have dimension S over analysis of J of F H Frobenius number plus H is not greater than H minus type H minus 1. Note that if H is symmetric, then this was just H. And equality holds for some H in H plus if and only if. So if and only if H is almost symmetric. Okay. Okay, so since IH is contained in annihilate of and since the base of KH over TH is given by Affiliation, the basis of H over annihilate of JH, FH plus H is given by the Affiliation, but H is less than FH plus H in H. So this is this set. Oh, sorry. Oh. And if pseudo-Frege number is F1 to Ft with T equal type H, and the last one is FH, we denote also PF prime H is pseudo-Frege numbers other than Frobenius numbers. So if F is in pseudo-Frege number, then F plus H is in Affiliation, and since F plus H is not less than FH plus H in H, so this is so contained in X, and so this in containment, yeah, so this set as cardinality is H minus type H minus 1. Okay, and we have the inequality. And if equality falls, then since FH minus H, not FH for any pseudo-Frege number, we must have FH minus H is contained in PF prime H for any F in PF prime H. So this implies that H is almost symmetric by the result of Hirokatsu-Nari. Hirokatsu-Nari theorem says that the H is almost symmetric if there is a duality of pseudo-first numbers, namely, so if f is in pseudo-first number not equal to Froebel's number, then Froebel's number minus h is also in pseudo-first number. This word. Okay. Okay, so we take time. So we also want to construct symmetric from n to n to nte and make adding n1. So we want to make some symmetric h, but this is so in not in final form, and so I skip this today. Okay. So it is. So, let's talk about similar semigroups with small multiplicity. And if symmetric and the multiplicity is small relatively E, then putting J is J of F, FH plus N1. So this annihilator has, so dimension is missing. So annihilator should be, this should be dimension of K. And so, and just must contain x2 to xe. The possibility of J is very limited. So, for example, if E equals 4 and MH equals 6, so then by this condition, this dimension of this thing should be 6. And so since E equals 4, and so we have 1. So since A equals 4, then dimension 3 in degree 1. And since Gorenstein, the circle must be then dimension 1. So, and so Colen's 6, the possibility of J is unique. Y squared plus dw. Note that in this case, Y is, of course, Y is not the biggest, but need not be smallest. But so seeing the table of symmetric semigroups of equal 4 and multiplicity 6, so you can compute. So the second one, so any shape. Second one is, so for example, choose this one. So multiply, see, 23 times 3 is 69. That equals 32 plus 39, 37. Okay, so every member satisfies this condition. So I'm not sure such is so done by before or not. Maybe Pedro knows better than me. And then, so let X be as so MH and put J equal J of F H F1 Frobenius number plus N1. And if N1 is not greater than E plus 3, the possibilities of J can be easily listed. And so let's show the case of N equal E plus 3, and then if E equal 4 and multiplicity is 7, and if we assume 7 is less than N2, less than N3, less than N4, then J is one of the following. So there are, since we have the fixed order, then we have 4 candidates. And so again, thanks to gap, and we can list all symmetric semigroup of multiply 7 up to a certain point. And so, for example, this C means 7, 8, 9, 13 satisfies this equation. So 13 times 2 equal to 8 plus twice 9, etc. So it is very interesting that ABCD is all coming out. Okay. And so since I'm lacking time, then so if Frobenius number plus N1 has unique factorization, then it is very special type. And so if H is symmetric and FH plus N1 is unique factorization, then N1 is product of these numbers. And H is a computation of special type. We can construct this by successive gluings with N and K. H is obtained as X. So X2 minus X1 the power X3 to the power minus X1, X2, X4 times to the 1 minus X1, X2, blah, blah. And so perhaps we can prove this by using a simple number. So this is my second paper, so published 38 years ago. And so we talked about gluing, but since we have not much time, so we can compute inverse polynomial of gluing by this formula, and so we omit the detail. And so another proof of Brzezinski's theorem for Gorenstein of E equals 4. So Brzezinski proved that if E equals 4, that is codimension 3 Gorenstein and symmetric, then either the number of generators is 3 or 5 in 1975. So actually, to tell the truth, I couldn't follow his proof. Perhaps, I didn't have enough guts. But so for 30, what years, I wanted to find some proof I can understand, I can follow. So and succeeded to find a new proof using Book-Swarm Eisenberg structure theorem. So you can find this in archive. And so, okay, so I don't say that Brzezinski's proof is difficult for everyone, but difficult for me at least. And so, sorry, and so the key is if N1 to N4 is symmetric, which is not a complete section, then for some I, FH plus Ni has exactly two different factorization, and hence this inverse polynomial is a sum of two monomials. And for example, H is 12, 13, 19, 29. Then the is symmetric with Frobes number 59 and 71 is has exactly two factorizations. And but so and but take other generator. So if we take 29 instead of 12, then so we have inverse polynomial this. And but in this case, so since we have also we have three expressions, these three are collinear. So essentially, the dimension is 2. And so we omit the proof of 7.1. So this is exactly two different factorization is important. And so this uses Eto's previous work using Moscariero's low factorization matrix. So after seeing once some FH plus N1 has exactly two factorizations, the proof of Brzezinski's result follows from this theorem. And HB numerical semigroup of n-vector dimension E. So assume that this J of this is just exactly two monomials. And then so mu of this guy is at most E plus E minus S square over 4. In the case of E equal 4, this part is 4, and this part is at most 3. So 3 square is 9, and 4 over so and yes, this shows that in case A equal 4, this shows that at most 6. But since the number is known to be odd, then we have 5. And if if E equals 5, then the number of generators is at most 9. Okay, so this we can explicitly calculate the annihilators. So that J is the sum of 2 variables. And so this is difficult to follow instantly, but anyway, we have some bound. And so if E equals 5, and so inverse polynomial is sum of 2 monomers, then we can compute that mu of IH is either 4, 6, 7, or 9. Okay, and so we want to show the number of generators which, when the case symmetric and equal 5, but so if so inverse polynomial has only 2 monomers, then it is done. But so in many cases, yeah, the number has, okay. And so in the case multiplicity of 6, then so inverse polynomial is just this thing, and this, in this case, this is so minimal number of generators 9. And so we just so calculated, so as far as we have calculated, so if E equals 5 and H is symmetric, then the number of generators is 4, 6, 7, 9, 11, and 13. So we don't know the result yet. And so well, this is Brzezinski's famous example with number of generators 13. And so in this case, so J of, so since problem number is 101 and Ny is 90, this is just sum of 3 monomers. And so I hope we could, yeah, we could do some methods of calculation in 3 or 4 variables. But perhaps we guess in the case of equal 5, then essentially, so the number of monomers is so just 3, or at least in dimension 3. So, okay, so this is what I want to talk about just now. Oh, and okay, so these are the differences. Okay, thank you very much.
Okay, Keiichi, thank you for your very nice lecture. And this is an interesting application of inverse polynomials to numerical semigroups. Are there any questions? May I have a general question? Is there a method, an algorithm to compute the annihilator of an inverse polynomial, or is how you only? I mean, how does it a computer? Is it Gröbner basis technique, or what? How is it done?
So since the inverse polynomial has special type, but I should say we don't know the general method for computing yet. So for the case of sum of two monomials, so it is not difficult as you suppose. So we have not to use any method only by hand. Okay.
Yeah, but I mean, there is this program by Pedro and others, you know, and they implemented an algorithm to compute it, right?
Yeah.
And I wonder how one is it based on what? I mean, what is the technique?
Okay, so
you mean by for computing the factorizations of an element in a numerical monoid?
No, I mean, suppose, so
in fact, from the factorizations, you obtain the monomials and then you sum them up. So there are different ways. It depends. Sometimes we use normalies, sometimes we use 42, or sometimes we use what we call the grandmother's method, which is by hand. Is the spanning tree of all possible factorizations, just removing any of the possible generators that could be removed to that element. And then we get a spanning tree, and the leaves of the trees are precisely the factorizations. But depending on how big is the number, we may want to use normalies or 42 or even something. It depends. So you can use.
Is it after all? It's a linear programming problem, huh?
Yes, actually, that is the problem. Yes.
Yeah.
So it depends. It depends on how big is the number. If the number is big and you have many generators, then you are lost. Because if you have, for instance, if you want to use normalies, then you will need something like 2 to the number of generators variables to complete the whole thing. And then it becomes a bit nasty, But for small examples like this one, is done by hand. Let's say by hand may mean that you start removing things until you get to positive things or 0. And once you reach 0, you have a factorization, and you study all possibilities. Actually, what we use here is a command that was implemented in GAP, which is called restricted partitions. You can compute the partitions of an element of a non-negative integer with respect to a list of integers. And this is computed by pruning a tree and doing some heuristic. So it's just exploring a tree, which is, I think, is the fastest way when the number of generators is small.
I see. That's very interesting, So other questions to Teishi?
I have a question.
Okay.
So the Brzezinski's theorem was only for multiplicity 3.
Dimension 3.
Dimension 3. But do we know, I mean, is the relationship between the multiplicity and the number of generators of the defining ideal, is it known?
So
if
you want to fix
the multiplicity and then
well, there's an upper bound. Yes, there's an upper bound, which is reached by those with maximal embedding dimension. But this is actually say n over 2. Is n times, and E with the notation, with Keishi notation is E. E times E minus 1 divided by 2 is the maximum number of possible elements in the final yield. Yeah.
Okay, so the symmetric condition is making it efficiently generated by 3 or 5. Okay.
Okay. Thank you, Pedro.
Yeah, actually, this is another problem, actually, because this is for maximal embedding dimension ideals, but you can also think about what is the best you can achieve for symmetric numerical semigroups, and then the problem is different. And there are many authors that have worked on that.
Yeah.
And yeah,
I see.
Thank you, Pedro.
Okay. More questions? If not, then I would like to thank Keiichi once again for his very nice lecture.
Okay.
And
thank you very much.
Bye-bye.
Thank you very much.
Thank you. Thank you very much.
Yeah, thank you.